Okay, looks like we're going. Okay, so welcome back. So here's where we were last time. We just finished section 1.1, which is of course ultra short, and on to section 1.2, where we already did the first example, talking about parameterizations, right? Which is a function that gives position as a function of, I'm going to say time, right? And you don't have to, it doesn't have to be time, but it's awfully useful and convenient very often to think of that input single parameter as being time. So position is a function of time. So we talked about this one, and notice very explicitly we're giving position, namely coordinates x and y, right, as functions of time, right? Single parameter that we're interpreting as time. And said differently, we're giving the x-coordinate as a function of time, we're giving the y-coordinate as a function of time. And what we noticed was that all of these points satisfy this equation, and therefore, whatever it is that this is parameterizing, all the points are on the unit circle. And in fact, then we sort of thought through, okay, what happens at t equals 0, and what happens as t increases, and it's pretty easy to see this actually goes around the unit circle. This parameterizes the unit circle. Okay, so moving on. What do we have here? What is that? There's different ways to go about deciding or interpreting what this is. I'm going to show you a couple different ways to do this. One way to do this is to realize, first of all, that in the parameterization, when we have something like this, don't forget the first coordinate is your x. The second coordinate is your y. Right? So with that in mind, I can solve this first equation for t, and then I can plug that formula for t into the formula for y here, right? And then I have y equals to, well, what turns out to be then 3x plus 7. So effectively, we're just eliminating t from the parameterization. One way to think about it. Okay. So now this is one thing you can do, and having done this, you notice that what we conclude is, oh, hey, check it out. I know what that is. That's middle school. I remember that. That's a line, right? And so we know that this parameterizes a line. Now, here's a different move that you can do. Again, keep in mind that when you, and let me write this in a little bit different way just for convenience. When you have a parameterization, that's your first coordinate is x, right? And then your second coordinate, that is y. And another way that you can think of, trying to interpret, and this is just another tool for the toolbox. I'm not saying this will always work. Sometimes it won't work very conveniently. But anyway, another thing you can try to do is to take the formula for x and figure out what do you have to do to it. What do you have to do to it? I'm trying to switch to the other color. There we go. What do you have to do to it to turn the formula for x into the formula for y? And this is just kind of, playing games. I see I have to start with t minus 1, which is what x is. I want to get to 3t plus 4, because that's what y is. And what do I have to do to t minus 1 to get 3t plus 4? Well, I can start by multiplying by 3 so that this looks more like that. And then I see I have to add 7 to both sides. Just keep track of what you're doing. I mean, you've got to do legal algebra, of course, right? And out comes, you'll notice, the relationship that you're looking for. And notice it's the exact same relationship that we found above. So another tool for your toolbox. I like that metaphor, by the way, because tools are useful for certain things, but not for other things, right? And so it's not good enough to just have one tool. Sometimes you need a screwdriver, sometimes you need a hammer. So it's good to have various different methods that you're aware of and that you're thinking in terms of, because different tools are useful in different cases. Okay. All right. Okay, moving along. Now this is a harder one. Now we're in 3 dimensions. Someone asked on Monday about what happens if you get into 3 dimensions. So here is a 3-dimensional parameterization, which you can tell because you have an x, a y, and a z. All right, so this gives position XYZ, position in space as a function of time. So, what are we, how are we going to do this? And if you were to try to just write down a relationship, a single algebraic relationship that involves all three, X, Y, and Z, kind of analogous to what we did here. Here we have a relationship that involves both of X and Y, namely involves all of our coordinates. If you try to do such a thing here, it's not going to work. So again, we have to use different tools in our toolbox. What works in this case, I think this is actually pretty satisfying, but is to notice first of all, well, at least this part right here I recognize. That's we already studied that. That's a parameterization of a unit circle. Now that's not what we're actually interested in, but nevertheless, I recognize that those first two coordinates are doing the unit circle. So keeping in mind what that means, I'm throwing away the z-coordinate. I'm saying if I ignore the z-coordinate, namely if I project down into the xy plane, then what remains is the unit circle. So now that doesn't actually tell me what my curve looks like, but it does tell me that the shadow down in the xy plane is doing this, right? It's going around in a circle. Okay, so now I need to know what the rest of the, I need more information to be able to interpret what this is actually doing. So the second observation is actually much easier, and that is the z-coordinate itself. You can think of that as being the projection to the z-axis. And that one's really easy to understand. Z is just increasing with time. Z is literally t. Right, so now I understand two things. I understand what the projection into the xy plane is doing. The projection into the xy plane is moving around in a circle because of that business. And the projection to the z-axis is just sort of rising at a constant rate. And so now just use your sort of three-dimensional geometric intuition. What curve has a shadow that looks like this and rises at a constant rate? It's going to be a helix. Which is what we call this shape right here. So it shadow moves around in a circle. Altitude increases at a constant rate. What do you think? Everybody see how that works? See how it's different? Like this is a different argument than we gave in any of the previous cases, and because every case is different. And, don't think of it as we're learning how to solve different kinds of problems. Think of it as we're collecting tools for our toolbox that we know how to use and can therefore apply as needed in hopefully any number of situations. Okay. All right. Moving along. Now, the previous examples, we were given the parameterization, and the question was, what's the thing? What does it look like? What does it trace out? Here we're going to ask the opposite question. What if we're given what it traces out? What if we know what the curve is? And what we want to do is we want to create the parameterization. We want to do what's called parametrize that known given curve. So it's backwards of the previous examples. So there are different methods for this. I'm going to show you my favorite one first. It's what I like to call the graph parameterization, because if you have a graph, and by the way, we're going to talk about this in more detail later, but for now, just to be clear, what I mean by a graph is where you have one of the variables is a function of the other. Okay. So if you have a graph, the big trick, it's so simple. Let t be whatever the input variable is. It's that simple. Everything will just fall into place. If you let your parameter be your input variable and then follow your nose. So let me show you this in action. So here we have a graph, you'll notice. It's a graph because I have solved for one of the variables in terms of the others. We have y equals. Right? So what's my input variable? Well, my input variable then is x. Per the rule, we're going to let x be t. Well, I mean, here's the thing, though. If x is equal to t, then I don't really have any choice about what y is going to be. I mean, if x is t and if y is x squared, then I'm really kind of forced that y has to be t squared. And check it out. We win. We just parameterized, right? We now have position as a function of time. So it's a wonderfully simple trick, this graph parameterization. You can parameterize lots and lots of stuff because all you got to do is the thing that you're parameterizing just needs to be written as a graph. And right? Yes.
Is there any significance to the function being named x, like the vector x, or is that just...
This is just a shorthand on my part. Yeah, it's a great question. So we have a function here where we start with the t-axis, and then the function is giving values that are in the xy plane, and so we're giving position points x comma y are functions of inputs that are t, right? And I wanted to give a name to, well, what are these outputs? Very often we conflate the name of the function and the name of the output from the function. That's pretty common, right? So what am I going to call this vector that has coordinates x and y? And well, lots of choices, I suppose. I call it x, and it seems a little sort of asymmetric. Like, why don't I call it y? But I don't know, because the x is first alphabetically. It doesn't really matter. But
so could you call it like z or something? Or
sure. Well, you'd want to give it a vector name. Z would be awkward because it'd make it look like it was a third coordinate. But you could call it like P for point or P for parameterization. Or, a lot of options. I don't know. I settled on X vector a long time ago, and I kind of like it. But it doesn't matter. It's a personal preference. Yeah, good question. Okay, so powerful method. Let me show you how this can be helpful in a more complicated circumstance. And that is, what if you want to parameterize this curve right here? And I can't even draw that curve off the top of my head. What a weird looking curve. Right? And it's particularly scary because I look at this and I think, oh my gosh, I can't solve for y. But here's the thing. I can solve for x. It's really easy to solve for x. And once you have solved for one of the variables, right, you solve for one of the variables in terms of the other, then you can play the graph parameterization game. Namely, your input variable, again, your input variable here now is y. So let the input variable be your parameter. And then notice that kind of forces you into a formula for what the other variable is. And boom, we parameterized this curve. This curve I can't even draw, but I can parameterize it. So very powerful trick. Big fan. Definite. That tool should have a prominent position in your toolbox. Okay. All right. Now here's a harder example. There's a really powerful method underneath this. And again, the example here in particular is not the point. The point is the method by which we're going to analyze this example. And what we're going to consider here is kind of a bicycle wheel. You've all seen bicycles going down the street, and if the bicycle has a reflector, and if the reflector is, it's at night or whatever, and it's picking up light from the street lamps, etc., and the reflector will make this it'll kind of do like that. So we're going to parameterize that curve, the path of the reflector. And it's a weird path. I don't know that I could write down the equation of that curve. I literally don't know how to do that. I've never sat down and dedicated hours of my time to try, but at a glance it looks really hard and I don't want to. I don't think it's going to work out well to write the equation. But parameterizing is not that bad. So there's two tricks involved in the tool that I'm showing you here. First is to figure out how you can use vector algebra. So the thing that we're trying to parameterize, so this thing here, that point that moves along what we're parameterizing, can I view that as a sum or difference of vectors that are easier to understand? Is that a question? Yeah. Was that? Oh, I'm sorry. I thought that was okay. Yeah. Let's try to write this as a sum or difference, some algebraic vector algebra combination of things that are easier to understand. And in particular, that point I'm going to point out is the sum of that point, which I call A because it's the axle of the wheel, plus this vector that I'm calling D, because it's the difference between the reflector point and the axle point. So P, the thing I'm looking for, is A plus D. And I claim that A and D themselves are much easier to understand than P itself. Yes?
So vector A represents the axle, right?
Yes, that's right. A is the axle, and that's right. Mm-hmm. Yep. Yeah. Okay, so all we got to do then is kind of break down those individually, and let's understand the axle as a function of parameter, and let's understand the D vector as a function of our parameter. Now, before we can do that, of course, we have to decide what's our parameter going to be. So this is the second big trick, second sort of important step before you get going. Are we going to write this in terms of time? Are we going to write it in terms of angle? Are we going to write it as a function of distance traveled along the road? You've got a lot of options. You want to be very particular and specific about what are you going to use as your parameter. There's no magic right answers. In this case, knowing as I know how it's going to work out, I think a really nice choice is to choose this angle here. Like that. And roughly speaking, the reason I'm going to choose that angle is because, well, for one thing, you can see D right there is it's a direction. It's kind of going around in a circle, and vectors that point in directions are nicely understood in terms of angles. The other thing is this angle starts at 0. So keeping in mind that the reflector starts going straight down, and we're measuring this angle T from straight down. So we're starting at T equals 0, and then further, as the wheel moves, this angle T is increasing. And that's good, right? You want to parameterize things in the right direction. You don't want to parameterize things with your parameter moving backwards. That's weird. So anyway, there's my choice. That's what I'm going to call, what my parameter is going to be. So I'm going to write both A and D in terms of T. All right. So with the vector relationships written down, with my parameter crisply, clearly identified, let's start computing. So what can I say about the axle? I've already forgotten what color I used there. But anyway, here's my axle point. It's kind of a freebie that the y coordinate is going to be A because the radius of this wheel is A, and so the axle's at height A. That part's easy. The x coordinate, though, what's the x coordinate? The x coordinate is that distance. Well, what is that? That distance, I'll point out, is the amount of road that the wheel has rolled over. And the key insight, and again, every example is different, but the key sort of physical reality insight here is that I'm going to color code this, the amount of road that has touched rubber has to equal to the amount of rubber that has touched road. So that's just that's a physical intuition thing. If something is rolling, right, then if the wheel's not slipping, then those two distances have to be equal. You'll buy that? And what we have there in blue is easy to write down. The blue is no problem. That's the arc length of a circle of radius a, where the angle is t, and so that blue distance is AT, and therefore the green distance, namely the x-coordinate, also AT. All right. Okay. Now next, question.
How can you compute AT just from the angle?
That's a geometry thing. So angle times radius gives arc length. Old fact from high school geometry. Yeah. Okay. Okay, so now a reminder. Next thing we need to do is we need to figure out that difference vector. That difference vector, as this wheel rolls down the road, again, it's just kind of going around like this. Right? So keep in mind, we're talking about a vector. Vectors have direction and magnitude. They don't have location. So the vector there, that D vector, it's just literally going around a circle of radius A. So if you want to know where you are on a circle of radius A, no problem. Trig pretty much handles that for you. In particular, cosine and sine. Now here's the detail devil. The detail devil is that it's not cosine and sine of t. T is that angle. We chose t because it increases as the wheel rolls, and it's convenient for that purpose, right? But that's not the thing that you take cosine and sine of to find the vector we're interested in. This angle here is the thing whose cosine and sine give us d. So I have to write d first in terms of theta. And then I have to recognize theta and t are different, and so I'm going to have to think about a relationship between them. And I think it's a pretty easy pitch that the sum of these angles is always 3 pi over 2. 3 pi over 2. And so therefore theta is 3 pi over 2 minus t, and you take this formula for theta and you plug it in there, and you recall all of your angle addition formulas, by the way. I hope everybody has learned their angle addition. I know it's a long time ago, trig. High school trig, and I further know a lot of high school trig classes maybe let that one slide. I don't think that's a good choice. The angle addition formulas are really useful, and they come up very naturally in non-weird exam. This is a very natural example, right? So please make sure that you're good with angle addition formulas. That's how I got from here to here. Okay, yeah.
Could you have just, instead of writing 2 over there and theta there, made the theta t and then change the first?
Yeah, you can. The problem there is that this theta, though, if you think about it, as the wheel rolls, theta is decreasing. Yeah. Or said differently, as theta increases, the wheel rolls backwards. Mm-hmm. And so if you care about which direction you're parameterizing the curve, and sometimes you do, sometimes you don't. If you do, then theta is not a good choice because it's going the wrong direction. It's decreasing, not increasing. But yeah. If you don't care about the direction of the curve, then absolutely. Okay. Yep. All right. Okay. So and then it's all over. This is our A, and this is our D, and as previously discussed, the point that we're parameterizing is the sum of those. So win. Okay, so lots of details. Try not to get bogged down in the you do need to understand the details, right? But also, in addition to understanding the details, try to step back and realize the big picture is we figured out a way to view a complicated vector as a sum of simpler vectors. And then analysis follows. Okay. All right, here's kind of another example of that. If you want to parameterize a line. So let's see here. For example, here's a line, and I could look at the vectors representing points on that line, and if you look at all of these points here, those vectors, the direction keeps changing. The magnitudes are changing. I mean, those vectors by themselves is not particularly clear how to relate them. But this vector, if I just have suppose I am given a point that's on the line that I'm interested in, that's not changing. That's given. It's fixed. It's easy to write down because it was given. And then these vectors, like this, also easy to understand because they are scalar multiples of the direction vector that I was given. So the points in question, right, these purple points might be hard to write down sort of immediately, but blue plus green is easy to write down, right, because, again, the green vector is a clear multiple of, always a multiple of the orange vector. So, nice little trick. And this is, by the way, this particular example actually is something you want to make sure you remember. Parametrizing a line, very useful. You can write it as x naught plus tv. And furthermore, anything that you can write as x naught plus tv is a line for similar reasons. Okay. All right. Again, more tools for your toolbox. Suppose you want to parameterize something. Let's say this ellipse here that we have an equation for, let's say. Sometimes, again, not always, exceptions granted, use, right tool at the right time, right? Sometimes what you are trying to parameterize is known to be a deformation of something that I already know how to parameterize. And specifically, I already know how to parameterize the unit circle. That was our very first example. Another good one to make sure you have pocketed, ready to go. Cosine sine, easy to parameterize the unit circle. So the deformation's pretty clear, right? What we're going to do is we're going to take our unit circle, there it is, cosine and sine, and I clearly need to stretch by a factor of 3 in the x direction, so okay, there you go. I literally stretch out the x coordinates by 3. And I need to stretch in the y direction by a factor of 2. So, okay, cool, let's do it. Multiply all the y coordinates by 2. And bam, there you go. So we have parameterized our ellipse by just simply deforming the simpler unit circle that I already knew how to do. So, sometimes this is a really useful trick. Everybody with me? Okay. All right. Okay. Parameterizations. Our book and many books refer to parameterizations as parametric equations. I find that awkward because a parameterization is really very, very different from what we typically call an equation. In particular, keep in mind, what is a parameterization? Position as a function of time. Right? So said differently, in a parameterization, the points are outputs. Parameterizations generate points. That's not what equations do. Right? Very importantly, equations, classically you talk about the equation of a curve. An equation is a point tester. You take points, x comma y, you pop them into the equation, and the equation either works, in which case, yes, that point is on the curve, or the equation doesn't work, and no, that point is not on the curve. Right? So these are structurally very different things. Equations test points. Parameterizations generate points. They both have their uses. I'm not saying one's better than the other. I'm just saying that they're very different. So that's why it just kind of this is nails on a chalkboard for me when they use the word equation, when they say parametric equations, when these two things need to be contrasted, not related, contrasted. They're different. Let's call them different things. Personal preference. So I always call it parameterization. The book and other books will say parametric equations. Just anyway, be a heads up. Don't fall for that inadvertent conflation. Okay, so the way we can take advantage of this observation is with the next example. So suppose you have a curve. There's a parametric curve, and I want to know, where does that parametric curve intersect this plane? So first thing I want to observe is I'm given a point generator and a point tester. So what I'm going to do is I'm literally going to generate points with the parameterization, and then I'm going to test them to see if they landed on the plane or if they didn't land on the plane. So where do I do that? Well, I generate points with the parameterization. Those are my generated points. Parameterization generates points with coordinates x, y, z given by these formulas. And then I test these points by plugging into that equation. Right? So I'm going to take 2 times x, this x, plus y, this y, minus z, this z. Right? I'm literally going to plug those in, and that test turns into this, which I can just straight up solve, and there you go. There's the t. 2 values of t, as it turns out. And what that tells me is that these are the values of t that generate the points of intersection. Now, the points, let's keep in mind, I was asked not for what values of t, I was asked for what points themselves. So yeah, I am going to have to plug the solved for values of t into the parameterization to get the actual points themselves, sure. Right? But it's all over for the shouting when you get those values of t. What do you think? Everybody good? Okay. Again, what I like about this example is it really capitalizes on understanding the distinction between how parameterizations describe curves and how, in a fundamentally different way, equations describe curves differently. Okay. All right. Okay, last thing we're going to do in section 1.2 is talk about symmetric equations. I think some of y'all might have seen this before. If you have, super. If you haven't, no worries. It's a pretty straightforward idea. Again, here's our parameterization of a line in R3. Parameterizations are point generators. You can see it right here. You've got to give me a value of t. And with a value of t, I can plug in and, arithmetic, and out comes a point that I've just generated. What if I don't want a point generator for that line? What if I want a point tester? How would I create a point tester from this point generator? Now, it's going to be tempting to say, how would I find, therefore, the equation of this line? Turns out you can't. There isn't a single equation. So it's going to turn out, in fact, you can look down at the bottom, you can see it's actually going to be 2 equations. But nevertheless, the form that it takes is not the point. The point is I want to find a way to view the line from a testing point of view, not from a generating point of view. Okay, so how do you do that? It's a pretty straightforward process. The way I would test whether a given point is on the line is I would ask, is there a value of t that makes that point the generated point from your parameterization? Oh, and here's more math lingo, sorry. Recall from last time, that means there exists. So this says there exists a value of t. And then this little symbol here is shorthand for such that or so that, something along those lines. So This is saying we need to know that there is some value of t that makes this equation work. That's how you would test. Now that's a bad test because, question, does a certain value of t exist? I don't know. T is just some random thing that I make up that I plug in here. I can plug in any value of t that I want. Am I going to have to sit there and plug in all possible values of t until the point generator happens to spit out the point that I'm testing? That would be far too tedious. So the clever move is to solve for t in each of the three equations of this parameterization. And keep in mind there are three equations here because there's the x equation in which you can solve for t to get this. There's the y equation in which you can solve for t to get this. And there's the z equation in which you can solve for t to get that. Right? So you're literally solving for t in all three of these equations. And here's the thing, it's much easier to understand now. If I want to know, is there a value of t that makes this work, I could rephrase as, is there a value of t that makes all three of these equations work? And it's so simple. Is there a value of t that's equal to all three of these numbers? If and only if those three numbers are all equal to each other. Right? I mean, think about it. This is silly. But what if the green number were 6, and the blue number were 4, and the orange number were 4? So 6, 4, and 4. Is there a number that's equal to all three of those? Well, no, don't be silly. Of course not. Right? So I just need all three of them to equal. And having all three of those equal to each other is a point tester. And you can take your x, y, z that you want to test, plug into these three things, make sure they're all three equal. Did I see a hand over here? Yes.
Can this only be done if A, B, and C are not 0?
Yeah, the algebra is going to work out a little bit differently if one of those is 0 and So it works out just as well, but it works out a little bit differently. So in particular, if let's say which one? Let's say C is equal to 0. Let's say. Well, if C is equal to 0, then that says that Z is just equal to Z naught. That's already part of a test. And you can just plug straight in. The point that you gave me is the Z coordinate equal to Z naught, and it either is or it isn't. And then you just do the analysis that we just talked about for just the other two coordinates. Yeah, right. Okay, so a side note, this is called the symmetric equations for the line. So we start with a parameterization. We end up with the symmetric equations, and this is the process. Which, again, reminder, you ask, is there a value of t? You resolve that by solving for t, and then writing down sort of the obvious answer from that. Okay. So y'all may have seen, show of hands, by the way, I'm just curious, how many, did y'all's section of Math 218 talk about symmetric equations? Some yeses, some nos. That's interesting. Okay. All right. Okay, so dot products. Now, I'm quite sure that y'all have seen dot products. So I'm going to do, again, mostly review here. Here's the formula. I know you know this. There are a bunch of properties of dot product. They're in the book. You've seen them before, right? But again, give that a review. Just keep in mind, there's a lot of stuff. I might not always actually write this down or verbally say it in class, but anything that's in the book that's not explicitly excluded on the content syllabus is stuff that you're responsible for. And if I don't cover it in class, then it's either because I think it's a pretty straight read, or it's something you've seen before, what have you. But anyway, make sure to review all of these properties. I'm not gonna talk about them in class, though. Quick reminder: one of the reasons that inner products are important is that they are the model for inner products. And there's some really powerful things that you can do with inner products. And you might have even seen some of that in your linear algebra classes. But ultimately, Fourier series can be thought of as a simple calculation with inner products. And your instructors may have mentioned, and this is really cool, but image compression. Some of the important methods of image compression are ultimately just clever little observations about a particular inner product. So really cool stuff, very powerful applications there. Okay. Now, I'm going to take one little quibble I'm going to say with the book, but really my quibble goes farther than that. There are a lot of books and such that they use terminology, I think, in a confusing way. These words, perpendicular and orthogonal, they're different words. There are ideas that they refer to. In fact, there are two importantly different ideas that we need to relate to that could be viewed as either of these words. And unfortunately, sometimes a book or a person in casual conversation will use these terms kind of interchangeably when really they shouldn't be. We've got two distinct ideas. We have two words with which to describe them. Let's attach one to one and the other to the other for clarity. So in particular, to me the word perpendicular, this is a geometric word. This refers to directions. Two different directions being perpendicular, namely that the angle between them is 90 degrees. So notice how geometric that is. We're talking about directions. We're talking about angles. That's all geometric. So perpendicular is a geometric thing. Orthogonal, to me, is not a geometric word. To me, this is an algebraic word. This means the dot product is equal to 0, or more generally, if you're in an inner product space, that the inner product is equal to 0. Now, very often, these are the same, right? One of our big tests. Hey, here's two vectors. Are they perpendicular? Well, let's compute the dot product and see if it's 0, right? So they're very closely connected. The difference is that if you have two vectors, and if one of them is the 0 vector, right? So it doesn't have any length. There's no such thing as perpendicular. Right? Perpendicular is a relationship between directions. The 0 vector doesn't have a direction. So there's no such thing as being perpendicular to it. You see the problem, right? Now you can be orthogonal. In fact, everything's orthogonal to the 0 vector because the dot product is 0, and that's what orthogonal is. Again, orthogonal is an algebraic thing. So when you have the 0 vector involved, it's not perpendicular, but it is orthogonal. So that's the difference between these two concepts. So again, when we have two different concepts and we have two different words, we should associate one to one and the other to the other, and we shouldn't conflate them. Which again, unfortunately, this is very common, I'll say. Okay, so that's again one of my little personal pet peeves. Okay, hopefully y'all know this next one already. If you have a non-zero vector, then there is a unique unit vector that points in the same direction as that vector, and here's the formula for it. You take whatever your non-zero vector is, you divide it by its own magnitude, and that will give you the unique unit vector pointing in that same direction. Show of hands, y'all seen this before, I hope? Yeah, cool, good deal. Okay. Really handy trick, just comes up all the time, so make sure you remember that little trick. Hopefully you've seen this idea of a component. On the next page, by the way, we're going to talk about the idea of a projection. Again, we need to distinguish between these. The difference is the projection is a vector, while the component is not The component is just a distance. I can't say distance is an intrinsically positive thing. Components are not necessarily positive. So it's a scalar, though, not a vector. But the calculations involving components and projections they involve the exact same picture, and so it's again easy to conflate them. So be careful. Components a scalar, projections a vector. All right. So how do you compute that component? And the idea being that we're looking in a direction defined by one vector, and we want to know our other vector here, the one I'm calling W. I want to know to what extent does that W vector point in the V direction, where I say I'm totally uninterested in the extent to which W points perpendicular. I don't care about that. I want to know how far does it go in that direction. And my favorite example of this is, say, I think about a football game, right? And if the ball starts here and the ball ends there, did you make this many yards? Nope, you didn't, right? Throwing the ball laterally over there, right? That's not yardage, right? Yardage is how much did the ball move downfield. That's how many yards you picked up. So it's literally a component. Okay. There we go. Okay, so with that noted, we have a little bit of easy trig. Again, trigonometry is in the prerequisite trail for this course, so make sure you're good with trig. So there it is. And then notice that you can solve for component in that equation. You get this. And then there's a real clever little move here where I take this thing that I know is the component, and then I multiply and divide by the magnitude of V. That's legal. Right? I didn't really do anything there. I just multiply and divide by the same thing. Perfectly legal. But having done so, I then notice that the numerator is the dot product, and dot products are much easier to compute very often, at least if you know the coordinates. And so in this formula here then, previously for components I would need to know an angle, I would need to do trig, I would need to compute a magnitude which involves square roots. That's annoying. And okay, sure, fine, I still have to compute a square root down here, but notice that the angle and the trig disappear. Dot products are computed with 4-function arithmetic. Three function arithmetic. Right. So very convenient. Okay. So this is a good formula to make sure that you know if you want to compute a component. You want to make sure to know that formula. I personally do like to rewrite it a little bit. I think it's very convenient to notice that magic unit vector, that's the unit vector pointing in the direction of V. Check it out. Here it is. It's right there in my formula. And so in 2 seconds, I can rewrite this formula for component. I can rewrite it like that. And so what we get then is that this component is just a dot product with the appropriate unit vector. And I think that rolls off the tongue really nicely. So I even like to underscore this. Components are dot products with unit vectors. Rolls off the tongue really nicely. It's a really easy way to remember that formula. Yeah, you had a question in the back.
Yeah, so we were dealing with cosine of theta. I get that like the adjacent side is the component of that theta, but
yep.
How come the hypotenuse there is the absolute value?
Yeah, it's the magnitude. So keep in mind, so the cosine of this angle, if we've got an angle here, right? The cosine of the angle is that distance divided by that distance. And if you think about that, the distance is not the vector W itself. I need literally the length. And that length is the magnitude of the W vector. Yep. Good. Anybody else? Right. Okay. So really nice point of view, and I encourage you to think about it in these sort of verbal terms, components or dot products with unit vectors. Really nice way to think about it. Now to projections, this is actually very quick and simple, and the projection, it's just the vector in that direction. It's got the same magnitude, and so real easy formula for how to compute the direction. I'm going to take the component that I already know how to compute as the distance, and then I'm going to multiply by the unit vector pointing in that direction. And this then gives me what I want. This then gives me the projection, namely the that vector. I've just ensured that it's pointing in the right direction because I've got the right unit vector. It's got the right magnitude because there it is. And boom. So this I like to write like so. That's my preferred way to write it. The book does write it a little bit differently. The book likes, and this is they're free to choose on this, but they like to just replace these U's with how they're computed. They're computed as V over the magnitude of V. And then having done that, you can group together like this. And then they also like to, maybe just for sort of symmetry's sake, they like to sort of expand, that magnitude squared as V dot V. So you do get kind of a cool looking little formula there, but I contrast that with the, I think, much easier formula right here. And, between these, which one do you like? I don't know. I find this one easier to remember myself. I find this one easier to justify geometrically. And just a last really quick comment. I tend not to memorize things. I'm not really very good at it. But I'm really comfortable with understanding ideas and reproducing ideas to give me the things that I would have had trouble memorizing, right? So rather than memorizing this formula, I memorize the picture and the point of view of, it's a magnitude and a direction. So this picture, I remember, and I will always remember because it's a concept. The actual formula, I've never memorized it. I just rederive from the picture as needed. So I encourage you to take that point of view as well. Maybe in addition, right? Go ahead and memorize the formula too, right? But someday you will forget the formula. I hope that for a much longer time you'll remember the idea. Okay, and we're out of time, and this worked out perfectly on time. So we are done with sections 1.2 and 1.3 now. 1.1, 1.2, and 1.3, and I'm optimistic that the same in the afternoon, and we'll have that for the homework for this week. See y'all later.